Next, we'll go to process scheduling. The multi-program is to have some process running all the time to maximum CPU utilization. So what do you mean by multi-programming? Multi-programming is you want your CPU to execute one or the other task. We don't want the CPU to sit idle. So the main purpose is maximum CPU utilization. Along with that, time sharing. Time sharing is nothing but you might be having n number of processes. So you're shifting between these n numbers of processes. What is shifting? You're giving the control of CPU among this n number of processes for some time slot or time slice. Suppose we say process P1, P2, P3. So P1 can execute for 1 millisecond. Immediately the CPU will be shifted to P2 and the control of CPU will be given to P2. After P2's 1 millisecond, control of CPU has been given to P3. Like this it goes on. So that is your time sharing. So by doing all this, you can make sure that CPU is kept busy all the time. So to do this, process scheduler, what does it do is it selects an available process for execution. So process scheduler is the one who is going to select the process, which process can be given to CPU. So this process scheduling or scheduling, it requires some queues. So we have the job queue, you have the ready queue, you have the device queue. So what are these queues we'll see. So first one will come to job queue. So this job queue, which consists of the set of all the processes in the system. So in your system, how many processes are there? So all those processes will be there in your job queue. So we have already seen the process life cycle. So in that you can see the processes from the new state will be moving to the ready state. Okay, so we said when we are speaking about the ready state, so it consists of all the processes which are residing in the main memory and ready to execute. So there comes your ready queue. So from the new state you are going to the ready state. That time you have the ready queue. So where you have this job queue. So this job queues consists of all the process. So that is in your new state. So in your new state, what did we say? It consists of the process that has been created. So first you have the job queue that comes in your new state, wherein you have all the process of the system. Then you have the ready queue, that is where from the new state you're moving to the ready state, that is which and all processes are ready to execute, those are present in the ready queue. Next one, you have the device queue. So we said that when we are speaking about the life cycle, we said that now in the running state you have some process which has been executing. Suppose that process requires some input output operation to be done. So that time the process will be removed out of the CPU and it will be sent to the waiting state. So that waiting state is nothing but here we can call it as set of processes waiting for an input output device. So just take an example, printer. So you might be having some n number of processes. Suppose P1, P2, P3. All these processes requires the use of printer. So that time what happens? All this process will be placed in the device queue of the printer. Okay, so next you have the processes migrate among various queues. So in the process life cycle, we have already seen how a process goes through different states. So during this process, you can say that the processes will be moving among these queues, among these various queues. So you can see we have a diagram here which is showing us a ready queue and the various IO queues. So to begin with, we'll start with the ready queue. The processes that are placed in the main memory and are ready and waiting to be executed. So you can see here in the diagram you have the ready queue. So it is nothing but it is in the form of a linked list which consists of a head and tail. So the head or the header will be pointing to the first process, that is PCB. PCB is nothing but, we've already seen PCB is nothing but your process control block. So for each of the process, it is having a data structure that is called as process control block, which will be holding information about the particular process. So you can see here the head is pointing to PCB7, that is nothing but process P7, whereas the tail is pointing to PCB2. So according to this diagram, that is your process P7 is the first process, and process P2 is the last process. For that is what you can say, in the ready queue the first process is P7 and the last process that is waiting is P2. Okay, so that is represented as PCB7 and PCB2. Okay, so tail in the ready queue will be pointing to the last process, whereas head will be pointing to the first process. And among this PCBs, you can see here PCB7 is pointing to PCB2. That is nothing but it is containing a pointer that is pointing to the next PCB in the ready queue. Okay, I hope you know the meaning of PCB. So assuming that, we'll move to the next one, that is the device queue. So we spoke about device queue. So all the devices what we are using or what is being used for the system, it will be having a device queue. So we take an example of a printer. So you might be having three process P1, P2, P3, which requires a use of the printer. So those processes can be placed in the device queue. Okay, so in the diagram you can see you have unit 0, unit 1 for images representing your magnetic tape. So one magnetic tape 1 you have a queue, magnetic tape 0 you have a queue. Along with that you have a disk 0, and you have some terminal device that is represented as terminal unit 0. So you can see here for disk unit 0 you have the header which is pointing to PCB3, and you have the tail which is pointing to PCB6, indicating that in the disk or the device queue for the particular disk named as unit 0, the first process waiting is P3 and the last process waiting is P6, and among the PCBs you have the pointer. So PCB3 is pointing to PCB14 and PCB14 is pointing to PCB6. Okay, similarly for the terminal unit 0, both the header and the tail is pointing to PCB5, indicating that the device queue which is representing terminal unit 0 consists of only one process, that is P5. Next we'll move on to the queuing diagram representation for process scheduling. Okay, so what is process scheduling? You're selecting the processes so that you can give the control of CPU. Okay, so in the diagram you can see here you have the ready queue and you have the IO queue. So queues are represented in the form of a rectangle, and you have circle which is representing IO device as well as your CPU. So you can see here in the ready queue, so in the ready queue you have all the processes which are ready to execute. So from the ready queue a process will be taken and will be given the control of CPU. So process is executing. So from the CPU you have one arrow point in the right direction. So that is, your process can complete its execution, then it will move towards the right direction. Or when the process is executing in the CPU, any of the following events can occur. What are the following events? So first one is IO request. An IO request can come in. That is, just assume we have a process P1 executing in the CPU. So that P1 wants to perform some input output task. So that time it will be moved into the IO queue. And from the IO queue, so IO queue is nothing but your device queue. So it will be present in the device queue, and from the device queue the process can be taken and the corresponding input output device can do the operation, and once it is done and again it is sent back to the ready queue. So again that process will be waiting in the ready queue for its turn to get the CPU. That is one case. And the next one is from the CPU you can see another arrow mark which is telling time slice expired. So what is this time slice expired? That is nothing but each of the process can be given some time slot. Suppose, assume each of the process is given 1 millisecond to execute. So suppose you have P1, P2, P3. So P1 actually it takes 10 milliseconds to complete, but the time slice given is only 1 millisecond. So we were saying about time sharing. So what is time sharing? Each process is given some time slice. Once the time slice is done, immediately CPU is given to the next process. Like this it goes on. So time slice expired is nothing but the process has completed its given time slot. So then again it is taken away from the CPU and is again sent back to the ready queue. And the next case is fork a child. Fork a child is a process can create a sub process. That is a child process, and even after that case it will be moving to the ready queue. And the last option is an interrupt might occur. Wait for an interrupt to occur. In that case also the process can be removed out of the CPU and it will be waiting for interrupt to occur, and again once the interrupt is completed again it will be waiting in the ready queue for its chance to get the CPU. So this is the queuing diagram which is representing the process scheduling. I hope you have understood. If you have any queries you can kindly ping me. So next we'll go to the next topic, that is schedulers. So schedulers. So we know process will be moving across different queues. So we already seen ready queue, job queue, device queue. So process will be moving among all these queues throughout its lifetime. So operating system must select for scheduling purpose process from this queue in some particular order. So for to do this, we have different types of schedulers: long-term scheduler, short-term, and you have the medium-term. So long-term is nothing but you can call it as a job scheduler. Selects the process from the pool and loads them into memory for execution. So it contains a degree of multiprogram. Degree of multiprogramming is nothing but how many number of programs can be executed. That is degree. Okay. Then you have the CPU scheduler. So this job scheduler is nothing but where it comes. It comes from new to ready. Okay, their job scheduler comes to picture. From ready to running, CPU scheduler comes to picture. That is, you're taking from the ready queue, you're taking some process and you're giving to the CPU. That is it, moving to the running state. Next, they're speaking about IO bound process and CPU bound process. So when you say processes, it is a combination, it can have a combination of input output related task as well as some computation related task. If a process spends more of its time doing input output operation, then you call it as IO bound. If a process is spending more of its time doing computation, then you call it as CPU bound. So we can say system with best performance means it should have a good combination of CPU as well as IO bound. Why we are saying this is, if you have a process which is only doing IO bound, then what happens? CPU is going to sit idle. It is not having any job to do. So for a best performance, you should have a good combination of CPU as well as IO bound process. Next scheduler is your medium term scheduler. So what does this medium term scheduler do is removes process from the memory and it is reducing the degree of multiprogramming. So this is a scheduler which can be placed as a intermediate or intermediary. So process can be introduced. So sometime it is required for us to remove some process from the main memory. So in that case you can go for this medium term scheduler, that is swapping. So again we are going to learn about the swapping in a later coming point. So you can see in this diagram about the medium term scheduler. So we have already seen the half part of this diagram, that is from the ready queue process is taken and given to the CPU. So end is nothing but the process completed. So you can see here from the CPU you are removing some process out, that is swap out, and partially executed process. So here you can see the medium term scheduler coming to picture, and later point of time again you can put it into the ready queue, that is nothing but your swap in. And we'll move ahead to the next.